Hello, everyone. You're listening to Distant Radio 3305. This is Nightfall Zero, and welcome to another episode of Dangerous Cosmology. This is a historic episode for a historic moment. We all know what happened today and what was revealed. And that is exactly what we are going to talk about. Here with me today is, as usual, that Michael,
Hello.
handling the technical side of things. Selfish Pie, handling
Hello!
very little, as usual, but
handling the international Scottish
Whatever.
thing.
yes. And this, of course, wouldn't be a science show without our Dr. Shoba.
Hello.
Hello, Shoba. Welcome. Thank you for taking some time for us today, even if I'm sure you would be otherwise busy talking science with your colleagues today. Instead, you decide to be here.
My colleagues just left for Hawaii today, all of them.
Who did?
All my colleagues, except one.
To Hawaii to celebrate?
No, to observe even more interesting stuff.
Right. While you stayed here just because of this show.
Absolutely. No.
Exactly. No.
But
What do you mean, no?
I'm here.
That's what you told me earlier.
And I go observing in July.
Yeah, no, but still.
They don't really need 5 people on one telescope, you know.
Yeah, but I thought we were important to you. It's, you know, I
would
thought
never
that...
miss the show, obviously.
Okay, great. So that's why Commander Shoba stayed here instead of going to Hawaii, because she wanted to talk to us, with us, about this amazing discovery. Because
yes, it's a great day.
Indeed, it is a great day, because what happened today?
The first picture of a black hole was revealed by the Event Horizon telescope.
Indeed, that wasn't really I mean, you're not very charismatic. You should put more emphasis on this thing.
That's what you're here for.
No, I was trying
That's my job.
Yeah, because
I'll
I
do
speak well. You keep me here because I know science.
I was trying to build
Just
up.
give me the signal and I'll overreact. Or well, no, in this case it's not overreact. Do you know what I mean?
Yeah, anyway. So yes, I'm pretty sure that everyone who is listening to this show tonight has seen the picture. It's been all over the news since it was announced at 2 p.m. UK time. There were 6 press releases all across the planet, and I believe that Michael had an actual stream live.
Yes, we covered it on the radio, of course.
Yes.
And the entire planet is talking about this. Myself, as I was in the office today, I tried to engage all my colleagues about it, until someone said, "Oh, you are really into astrology, aren't you?"
Oh my god.
And I was like, okay, never mind. I just watch it myself because you're hopeless.
That physically hurt. And the thing is, I know what you're talking about as well.
Yeah.
Like I was trying to explain it to my parents last night, my family last night. And my sister, as soon as I said Sagittarius, my sister said, "Oh, like the star sign." It's like, oh, it like
that happened. That happened last week when I mentioned, "Oh, they're looking at the constellations." Yeah. Sure. Anyway, enough of that. So this picture, indeed, many of us, we were expecting to see indeed Sag-A. I, for one, was hoping for it. And correct me if I am wrong, Shoba, but we also know that the EHT was had Sag-A as the main target.
Absolutely. A lot of people were expecting Sag-A today.
Indeed.
But what we got was even better.
Well, that is debatable.
I think so.
That is debatable. Sag-A would be a bit more intimate, all right? At least to me, especially since we recently saw it in Elite. So it would have been a nice thing to discuss. But instead, we got M87, which is extremely larger than Sag-A.
Absolutely. Right? It's about 1,700 times bigger than Sag-A in terms of mass. And so even though it's about 2,500 times more far away than Sag-A, it appears about the same size on the sky, only about 2 times smaller across. So it is the only 2 black holes we can see realistically from Earth with current technology. So it was really the only 2 options. And M87 had been, I guess, we had less updates on it from the Event Horizon Telescope over the last years. So it was kind of a side project, or at least that's how many people saw it. It was
M87. Evan?
M87.
M87 was like the side check.
Well, it's more that with Sagae, we're getting updates very regularly. Every time they added a new telescope into the mix, they published the latest, best constraints on it. The last time we had an update on Sagae was only 9 months ago, and that showed that they were getting very close. While the last time we had an update on this one, M87, it was about 5 years ago. So since then, no news. We assume they were focusing on Sagae.
Yeah, they were just trolling.
No, they just got lucky, and it turns out M87 has a very active black hole, and because it's active, it's also very actually many reasons why it. In the end, they only needed 4 days of observations to make this picture. While with Sagae, they've been going at it for months. And they don't have it yet.
I was confused about that with the time frames, because it was just 4 days for M87, wasn't it?
Yeah, so they spent a few months calibrating the instrument, so they were checking already known objects far away in the universe to make sure everything was working fine. But the actual data, when they pointed to it, was only about 4 days. And then almost 2 years to process the data and understand what it all meant.
All right.
So, indeed, we got M87. It has been described as a monster of a black hole. I'm not sure how accurate the articles I read are, or if the quotes are actually on point, but scientists have been quoted saying that it is one of the largest and most massive black holes that we believe exist, like in the entire universe. I'm not sure how accurate this statement is, because I'm not sure how we could test this. Because, from our point of view, at least from my point of view, Sagae was already pretty big. Knowing that there is something else, just
on my end, but I don't know if it's just on my end, but there's a lot of splicing going on.
A lot of what?
Splicing. Well, it's not really splicing, but like you're getting cut off when you start and stop a sentence.
Is anyone getting the same issue, Michael?
No, not really. I'm
Jesus
wondering.
Christ, what is wrong with my? Oh, that's what. Hang on, sorry, that's my bad. I'll be a second.
Anyway, I was saying that. Thinking that there is something else out there that can just be very, very much bigger, it's just mind-boggling. I mean, it's really hard to imagine Sagae, and imagining something that big is just... I can't even start. But the thing is, we may be getting pictures of Sagae in the future, right? Because I believe that during the press release they mentioned that they're just that is another very likely target.
Yes, I mean they've been going at it for years with Sagae. It was, I think, the most likely target to get a good picture of, and they're going to continue with it. They said in the press conference very soon. Well, that could mean anything from a few months to a few years. Although we did get, I think that was one of the questions someone asked on the Discord. We did get some updates on the status of Sagae. We know that one of the reasons why they don't have the picture yet, there's many reasons, but one of them is that it's actually varying from day to day. Sagae looks different every day they look at it. It varies very quickly. Because basically the structure around it is not stable. It's not always the same brightness. It doesn't have a lot of mass currently falling in. And so the distribution of mass is still changing very, very quickly around it, which means they can't easily stack all their images together. Especially since they're not actually observing pictures like a slow-mo. They, like we explained last week, they observed this related transformed form of the data, which is the Fourier transform, like a compressed version of it. And that changes in a very different way than the image changes. So you definitely cannot stack the compressed version to recover the image that you see. So it might take a lot more time to get that right. So we know that Sage varies. That's at least one new piece of information.
We will get to the questions soon. As usual, we are taking questions live, both in the Dangerous Cosmology channel on the Distant Radio Discord server and in the Astronomy channel, which, not surprisingly, it is quite active today. So if you have any questions to ask live to our Commander Shoba, now it is the time to write them down. But before that, let's just open up the picture itself and let's just, analyze it. Let's try to figure out what we are actually looking at here. Because if you guys are watching the stream, maybe Michael is putting up a picture now. Yep. If not, if you have the chance,
already.
I mean,
it's up already.
I basically have this picture engraved in my head already. But many times I've seen it, but. If you have the chance, just open it up, and if you have any questions about why something looks like it looks, feel free to ask, and our doctor will answer. So what we're seeing here is a donut of fire, right?
It's a donut of fire.
It's a fire donut, or a lava donut, or something like that.
But first thing, the color red is completely arbitrary, right? So the way the telescope works, it only looks at one frequency of light, only one very specific color, but it's not a visible color. It's not literally red. So it would be much more accurate to have it as a grayscale, just from white to black, where white means more light and black means less light. Kind of like night vision.
That would be ugly, though.
Yeah, but the color red was just picked. You could make it any color. If it's more bright, it means there's more light coming from there, of this specific frequency.
Because it's not, the kind of light we're receiving is radio waves.
Yes.
So it's not infrared, which we could say, it's red, because it's infrared, But it's not, it's radio, and radio has no color.
No, that's true, absolutely.
Cool, I was just spouting nonsense and I got it right. Okay. So the red is arbitrary. So if you want, you can just put it in Photoshop and paint it green if you prefer your wallpaper to be green. And that will be as accurate as the current one because they're all arbitrary.
Yep, it's the color that we pick.
Or if you want to be extremely pedantic and you want to show off to your friends and just print it out in a gray scale and say, this is how it should look like. A scientist told me. The picture they are showing on TV is a lie.
Not even white. It would be a contour plot with circles where the light is the brightest and then just lines. And that's how scientists actually look at these things.
Let's not be too pedantic. Okay, we still want to keep some friends.
Be a bit pedantic to show off, but not too pedantic to put people off.
Yeah, you still want some friends, otherwise. So we're seeing this. Let's assume that. Let's disregard the color, but I didn't know about it, though. It's a good thing to know. But again, what we're seeing here is a donut of fire, surrounded by blackness, because only a small part of the picture is actually lighted up. And at the center, of course, we see the event horizon. So, first thing first, this is gas, right? This is mostly gas.
Yes, nothing solid like a star could survive so close to a black hole. If it was a star when it fell in, by now it's completely distorted back into gas.
Okay, what kind? Do we know what kind of gas is it?
Scientists use the word gas in a very loose sense. Technically, it's gas and dust. So gas refers to molecules of the gas elements, helium, hydrogen, mostly. And then dust refers to everything else, or what we call metals, which are not hydrogen or helium. So things like dust of silicon, little grains of carbon, CO2, maybe some water, although not much, because at these temperatures, all the atoms get torn apart from each other. So you mostly have ionized gas, like fire, what fire is made of.
Plasma.
Okay.
Yeah.
And as we move out of the ring, we see dark. Is that actually part of the picture, or they just... I mean, is the black on the outside of the picture actually that?
Yes. So what we see in this picture, all the black on the outside, that's part of the field of view. The recoverable area of the telescope. So it is actually black.
Michael, stop eating.
And even if you go much further out, there wouldn't be radio waves. So there's a lot of extra structure on bigger scales around this, right? This is a very, very zoomed in all the way to the event horizon. But actually, we also have pictures of the larger scale. If you zoom out by 1,000 times, there is stuff around. It's just that the stuff around is much less bright and or doesn't emit radio waves.
Yeah, there is some smearing, or how do you pronounce it?
Smearing.
I can't English. Sorry, guys, I just can't. There is some smearing on the outside. You see that there is some like dimmer orange, like sprouting from the top left and bottom right. I guess those are just... Is that still gas that is being attracted, but it hasn't entered the orbit yet? What is that? It's just... I guess it's...
It could be, so we're not sure. It's probably not gas falling in. Usually it has to be quite close in order to be heated, but it could be being shuffled out, pushed. You know, this gas is not gently going into the night of the event horizon, right? It's very chaotic, even though it over the 4 days they observed it only changed a small amount. It did change even over 4 days. It's not just sitting there slowly being eaten. It's swirling round at almost the speed of light. And there can be turbulence. There can be bits of it being flung out, and all sorts of complicated, chaotic processes.
So that gas is, you said it is moving around at almost the speed of light.
Yes. Otherwise, it would have fallen in by now. So it's kind of a selection. It's at the very closest distance it's allowed to be. If it was any closer, it would fall straight into the event horizon. If it was any slower, it would also fall into the event horizon. So we're really seeing the pileup of gas that's just fast enough to escape. So it's just under the speed of light.
Some of it must be actually escaping, no? Like breaking free of the orbit.
Yeah, no? Just because of all the chaos, some bits can be flowing out. It's what you pointed out with the two flares on either side.
Those could be things going out.
Yeah, so actually I have a picture here of one of the models that fit. So I can post that maybe. So they run very high accuracy simulations of gas falling into black holes. I think they run hundreds of them, possible things that it could be. And they try to see which ones match the best. So this is one of the pictures from the paper.
Yeah, if you're listening to the radio, we are posting pictures in the Dangerous Cosmology channel. So if you have a chance to hop in there, you will see what we are talking about. I understand that, of course, we are a radio. Usually we don't rely much on visuals, but of course, today's topic is all about a picture. So I apologize if you're currently unable to check a screen, but it is really unavoidable tonight. And yeah.
So that's one example I just posted. I think one of the best ones that fit the best. So in the left, you see the picture of one specific day. In the middle, there's an infinite resolution simulation of what gas would do if it falls into a black hole. And on the right, they basically blurred the image, pretending as if it had been observed with all the extra
Wait, they blurred the middle
effects.
One?
It's not only blurring, it's called blurred. There's actually more effects that come into it. So they pretend that's what it is, and then they apply all the effects that would make it through the telescope to us, and then being extracted. So it's a whole
Wait, so
pipeline.
You're saying that the picture we see in the middle is very likely how it looks like?
It's one of the models that fit. Actually, they have quite a few. It's not, as you can see on the right, it's not like we can see much detail, but it's an example of it, and this spiral at the center and his arms kind of around.
Yeah, because one of the I checked the American press release, and I wasn't really impressed by some of the questions that the journalists asked, because at least a couple of them were about, oh, this picture actually looks like crap. Can't you get a better one? Because, you know, it's you say that this is, I'm quoting one of the journalists, he was saying, oh, you say that the event horizon is quite sharp and you can clearly see the details, but to me it looks very blurry.
Yeah.
Is this the best you can do?
I heard that question. I thought, like, you know, have you ever tried to zoom in on a picture that's not very great resolution? Yeah, if you zoom in enough, everything's blurry, right? But
so
so I just posted another example of the models that actually relates to what you're saying. So at the bottom, you can see, if it's on the stream, a white circle next to the images. You see the white circle in the bottom right? That's actually the resolution of our telescope. That's how much is blurred. That's like basically 1 pixel. That's how big it is. This image is about 10 pixels, right? So that's the accuracy of our image. So basically the pixel size is bigger than the event horizon on the picture. So it's not going to look completely black, because even if you put a pixel right on top of it, you're still going to get a bit of the sides, because that's just how big the pixel is. It's not infinitely high res. That's why it looks blurry.
Yeah, and I guess that's just what we can do, right? With the technology we have used.
Yeah, absolutely. So the Event Horizon Telescope is already a telescope of the size of the Earth. It combines telescopes both in Antarctica to the US to Spain, and it manages to combine the data as if it was one big telescope. So unless we go to space, we can't make anything bigger. It's already the size of the Earth.
Let's put a telescope on the moon.
I'll happily do that. In fact, if I make it to Mars, I'll happily build another version of the what was that telescope that was meant to be like 100 meters across and built in Europe or something? And it was ridiculous.
The VLT.
It's actually being built right now. It's the ELT.
That's it.
It doesn't do this kind of stuff. That's not radio. Very different.
I know, but like, just
anyway,
something.
Yeah, no, I just wanted to go back to the actual picture before we digress as usual, because that's what we do in this show.
That's a great topic.
No, we will talk. It's just that we could rename this show to digressing cosmology or something like that. But, anyway, so just go back to the actual picture. So, okay, we have seen, we know that around that picture there is the entire M87 galaxy.
Yes.
Which, if we zoomed out, we could see.
Yeah, well, we cannot zoom out.
Well, we can. We have taken pictures of many things around the galaxy, the jets that are bigger than the galaxy. Around the black hole, there's clouds of gas that we've seen.
Are they publicly available?
Yeah, they're online. I can try to look for them.
Another thing that caught my eye is that the bottom half is brighter. The bottom half of this donut is brighter.
Absolutely.
What does it mean?
It means that we're actually seeing it at an angle. So
I was thinking that.
Yeah, actually, that's exactly what's happening. And in their paper, they say they know the angle we're viewing it at. If it's flat, we're seeing it between 18 and 30 degrees from flat. So it's inclined by about that much. Not quite 45 degrees, between 18 and 30.
Because that's just how the galaxy is inclined compared to us.
Well, M87 is pretty much an elliptical galaxy, so it doesn't really have a disk. I don't think it has a clear disk anyway. It still rotates. It's a rotating elliptical. And it's not perfectly lined up with the rotation of its host galaxy either.
What do you mean? To see it. Yeah. What do you mean elliptical? Because I've only ever heard of irregular, spiral, and hot dogs. What do you mean elliptical? What's that classified?
I'll post an image into the Dangerous Cosmology.
You can. Yeah.
Okay.
Well, elliptical galaxies are basically galaxies without a disk. They're all puffed up like a sphere or like an ellipsoid. So they're either very young, like dwarf galaxies around the Milky Way, because they're not big enough to form a disk. So they're either very small or very, very big. And the very big ones, like M87, are actually formed, we think, by many spiral galaxies colliding with each other repeatedly until there's no more preferred direction, because many of them have merged into a big blob.
So they're so elliptical galaxies, some of them you could describe as sort of bubbles.
Yeah, they are bubbles. They're big spheroids.
But the fact that it is inclined, I mean, doesn't mean that we see it that much hotter. Because I mean, considering how far it is, and considering, of course, the accuracy of this telescope, virtual telescope we are using, the inclination is enough to justify that difference in intensity. You're saying that if it was just a bit more inclined, we would barely see the actual color at the top. I mean, yeah, Scaleios is posting some pictures. We can, for example, in the very bottom one, you can see it that the lower part is very bright, while the top one is fading away almost. If it was a bit more inclined, we wouldn't actually see the event horizon. We would just see a half sphere.
Like a crescent. Yeah, that can happen, but it's not actually, it doesn't change that much.
That's weird. I mean, let me just get this. Okay, a black hole is a sphere. Okay? So no matter the angle you look at it, you will always see a sphere.
Yeah.
So why rotating it shouldn't change?
Right, that's because the material around it, the gas that's heated, is actually arranged in a flat plane around it. So it's like a disk. The black hole has a disk of matter falling in, and we're seeing that disk at an angle. Of course, the black hole itself, the event horizon, is a perfect sphere, or almost a perfect sphere.
Right.
So it's the material around it that we see. And that's flat.
Okay, that was a stupid question. I could have realized that myself. So the accretion disk is like a galaxy within the galaxy in terms of shape, because
it's a bit more puffed. So it's not completely flat. It's a bit more. The ratio is a bit bigger.
It's a bit fluffy.
It's a bit fluffy. Actually, exactly how fluffy it is something we'd like to know. It's a bit unknown. So. Which is pretty cool. But yeah, one thing you said if it was a bit more inclined, we wouldn't see the back. That's not actually true, because the gravity of the black hole bends light so much that even if the disk was completely on the other side, some of the light bouncing off of the disk would still just skirt the event horizon and come out on either side. So even if you saw it side on, it would look like the black hole in Interstellar. You know, if any of you have seen that, it's you have the bit in front of the disk, you see it as a line, but the bit of the disk that's at the back of the black hole compared to you still see it, because the light gets bent all around the sphere and it comes out at the sides. So it looks like the letter phi, or the tube sign.
Right.
You would very much enjoy the Veritasium video that I linked.
I know, I've watched it.
Yes. It's not only the one on how to interpret the results here, but the one on spinning black holes. I mean, I need to rewatch the spinning black holes because I still don't understand it, and I hate that. But I really enjoy those videos. Fantastic.
Anyway, so you mentioned this before we started the show, that this picture is, in a sense, a bit incorrect, because the black hole is not that big, right?
Oh, no, but it's not incorrect. It's what you would see if you could see radio waves. It's not incorrect in that sense.
No, but
the size of the black spot in the center, that's what I meant, is not exactly the size of the event horizon. The event horizon is a bit smaller than that, although not much.
Yeah, so what we're seeing in this picture is the ratio of the actual event horizon and compared to the accretion disk is not accurate.
It's what we call the shadow. So the shadow of a black hole is about 2 times bigger than the event horizon. and it's because of the way light is bent. I think that's part of the Veritasium video too.
Yes.
And because material cannot orbit the black hole closer than 2 times the event horizon. If it gets any closer than that, it's the forbidden region. It will fall straight in, because no gas can escape if it gets at 2 times the event horizon of the black hole.
But
so the forbidden region has this shadow.
But the event horizon is by definition the limit that you can't. It's the point of no return, right?
For light, remember.
Yeah, but light is what we are using to see things, so that's what we care about.
Yes.
You see,
so
that is. I had the same thing, and I figured it out. It was the event horizon is the point past which nothing can return, but if you are just on the outside of the event horizon and you point yourself directly away from the center of the black hole and you travel at the speed of light, you can technically escape then. But
yeah, if you're outside, but that's what I mean. Light, we are using radio waves, so basically light.
Yes.
To see things, and light only disappears after it crosses the event horizon.
That is if it is.
Horizon. So
that is if it's traveling directly away from the event horizon. That's why there's this silhouette, because of the fact that if you were to shine a light onto the black hole, then, or well, I am not the expert here. So, Doctor, would you mind taking this? Because my explanation is probably going to confuse everyone here.
No, I mean you're basically right. So it's light can go all the way to the event horizon. If it reaches the event horizon, then only a very specific angle of light can escape. Right? If you're pointed slightly wrong, you'll still fall back in. So you have to be traveling exactly away, and so it's under completely perfect circumstances. Now, in practice, for a start, gas cannot accelerate to the speed of light, and you see less and less light from it as it falls in. So the last region at the center looks a lot more dark because there's no gas there, so you couldn't really see it with light. Gas can pile up, as we see here, around the black hole at some distance. That's about 2 times the event horizon. It stays there. It can heat up, but as soon as it passes that limit of stability, any matter will fall straight in much faster. So it doesn't hang around if it enters the forbidden region, which just means there's no gas there, so there's nothing for us to see, even if we use light to see it.
Right.
So the shadow is bigger for this reason, because there's nothing in the forbidden region.
So in this image, there may be light inside the black circle, but there is nothing to illuminate.
There's much less light, and right, and also because of the geometry, you would also see it less. So the efficiency of photons that reach you also goes down. So anything inside this would look black to your eye, even if you were actually there. That's what it looks like. It's a bit bigger than the event horizon itself. It's like a shadow that's a bit bigger.
Yeah, to our eyes, yes, but this is radio we're talking about.
Radio is also light. So
yeah, but to our eyes, it would be invisible anyway, right?
No, we could probably see it in visible light. It's very bright, very. It will probably be too bright. If you were actually close enough to see it, it will probably be as bright as the sun by the time your eye can actually make out the gap at the center. So you'd be blinded. If you get too far away, your eye won't have enough resolution to make it up.
So let me just point this out a second, because this M87 black hole is not just a simple black hole. It is, in fact, a quasar, right?
Yes, it's a quasar.
And that is pretty much what you do.
Yeah, that's why I was much more excited that it was this one instead of Sagae, personally. Because quasars are actually what I work on, and Sagae is not.
Because what we're seeing here, because the thing is, it wasn't really described as a quasar. In every article I've read today, the word quasar was not even mentioned once. And because I guess that it's really hard for the average person to understand what a black hole is. If you throw random words like quasar,
it's also a matter of technicality. So the word quasar actually stands for quasi-stellar radio source, because in every case we've seen a quasar, we don't even see the galaxy around it. We only see a very bright radio source that's completely small, like a star. That's how they were first found. People looked up in the sky and they saw these radio sources that look quasi-stellar, like a star, and they couldn't even see the galaxy around. So historically, a quasar means a small radio thing that you can't see the details of, like quasi-stellar. In this one, obviously, you can see a lot of detail, so that's technically not the correct word anymore.
So the word quasar is outdated because now we know what quasars are.
If there's more words that came into it. There's QSO, quasi-stellar object, not only radio but other wavelengths of light too. But the correct word for this quasar is an AGN. It's an active galactic nucleus.
So they're okay. You guys love acronyms, do you?
It's easier than saying active galactic nucleus 3 times in the same sentence.
Well, you see, I'm infamous for being a smartass, so I would love to use the full name.
Yeah,
but how many times before it gets old?
At least 13 times.
Now you see, I've never tested that.
Still, I haven't seen any newspaper mentioning AGN instead of black hole.
But they've mentioned the jets, right? A lot of places have mentioned the jets that are coming out of this thing.
I think they did.
Yeah.
On the press conference too.
Yeah.
Yeah, we can't really see jets here though, right?
No, that's way too zoomed in. Also, we're not entirely sure which part of the structure around the black hole is launching the jets. They could start very far in. Maybe it's the things we're seeing leaving.
Don't you think?
They could also be forming further away. Or maybe it doesn't have jets right now. I mean, that's possible.
Yeah, because I was thinking...
Yeah.
I was thinking if they had photographed jets, I would expect them to show them because, they're quite telling. The fact that they haven't makes me think that maybe they haven't actually seen them.
No, not really. So maybe even if it was currently launching jets, you wouldn't necessarily see them right in the center. So think of a blowtorch. If you're pointing a blowtorch or something, it's very bright at the tip of it, but right at the start of the nozzle, when the gas comes out, it's still invisible. It only gets lit up on fire further out from the source, even though the most heat and the fastest speed is in the center. And quasar jets could work a bit similarly. So they get accelerated from the center, but they only light up because of collisions with other things further out. So they could be still invisible, even to infrared.
Right, but...
Definitely radio waves. They would be invisible in the radio waves, very likely.
So let me understand. They took this picture, but do you think they have other pictures that are more zoomed out?
No.
Or this is just the fixed...
No, they can't. They can't. Every scale that's part of this picture takes a specific spacing of telescopes on Earth. That's how interferometry works. So if you want to see things at the specific scale, you need some maximum distance between telescopes. And the amount of area you can recover is completely set by that too. And because telescopes on Earth can't move very much, the same telescopes could not get a picture of any other resolution. That's fixed.
No.
Now, if they used only one of the telescopes, like say only ALMA, then they could take an image of a much, much wider field. But that wouldn't be the Event Horizon Telescope as a collaboration. It would be one specific telescope.
No, but that's not what I'm saying. Because, I mean, they're also watching Sagae, which is much closer than that. So they can't have the same zoom, otherwise...
No, they do. Sagae and this guy are about the same size on the sky. It's crazy, but that's how it is. Sagae is about, I said it at the start.
Oh yeah, because it's much smaller,
it's
right?
Much smaller.
It's
more than 2,000 times smaller, but it's also about 2,000 times closer.
So a picture would be similar, in terms of size.
It would be a bit better resolution for Sagae. I think it's a factor of about 2. In total, it's about 2 times easier to see.
Oh.
But it's also much fainter because they were very lucky with this one. As they said in the press conference, we know this quasar was more active in the past. It was brighter. So maybe if they had coated just at the wrong time, it would have been too bright and you couldn't see the center. So they coated just when it was bright enough to be easy to see, but not too bright to hide the hole in the center. Very lucky.
So this confirms, after 100 years, that black holes do exist.
Definitively.
This is pretty much
final proof.
This is pretty much what it says, because up until now, as I mentioned last week, we've science fiction and even science always spoke about black holes as if they were already proven, and they were mathematically and with equations, but they were never actually seen. So it's hard to realize, to think back, that until yesterday we didn't actually have proof. Well, we didn't. Scientists did already for years, but we didn't. We always assumed that they existed simply because scientists told us that they existed.
The
right?
public
now
no longer just has to trust that we've gotten the math right. They can look at this and say, "Oh yeah, they did that."
Yeah. No, I'm not. Of course, I'm not saying that. I mean,
we had proof that something of about the correct mass existed, compact and very small, but there were still some theories out there that are now ruled out, like wormholes. This thing, not a wormhole.
Why could it be a wormhole? It's a hole, right?
Yeah, but wormholes, that was simulated too. The behavior of space-time around the edges of a wormhole is very different. I don't think they have any pictures of it.
There's no worms in this hole. So.
Well, okay.
And it's not a quasi-star. It's not one thing that's very heavy, like a very exotic star made of strange quantum material.
So there is zero chance that this could be anything else but a black hole, how it was theorized by Einstein.
Yes, at this point, of all the simulations they ran, only the ones that include the physics of a black hole with the Schwarzschild radius, plus the physics of the gas when it falls in, of course, that's the only ones that matched. And let's not forget the ridiculously complicated physics of the gas falling in, right? It's actually much more complicated than just GR. Now, I've seen this hailed everywhere as a triumph for GR. It's not a triumph for GR, it's a triumph for the fluid dynamics that went into it. It's fluid dynamics plus magnetic fields plus GR. It's the most complicated simulations ever. You have to include effects from all the branches of physics into one, and everything has to work right.
This was obviously a extremely huge and successful collaboration, which I believe it was also said in the press conference I've seen is telling of what we can achieve if we band together and do things as one. Because it was mentioned that not like any single telescope that was used could even hope to achieve this without the help of others.
Yep.
And it kind of shows how efforts must be global if we want to actually break through.
It also shows that it's not that sometimes cooperation can achieve more than funding, because in the end, none of these telescopes were built specifically for this. They all already existed, built by different countries, and all it took was for them to actually work together for 4 days. It took 10 years, right, to coordinate and convince all these facilities to work together so that for 4 days they would all point in the same part of space and all share their data. That's all it took.
And we can only imagine what an array of telescopes built for this specific purpose could achieve.
It doesn't need to be, because individually they already do a lot. I've used some of them individually to look at stuff.
I don't know, absolutely they do a lot. But I was just thinking, I'm just imagining now, maybe it's not going to happen, but a series of telescopes in space built to to analyze quasars, how precise and accurate would they be, and how useful? We had the questions about it actually from Kenny, and as we mentioned before, this is pretty much your field. And how do you think that this discovery will help what you do? Like, is this going to change some of the current projects you work on, or is it giving you new ideas, or I don't know, how is you and your team, what changes from today considering this?
So one thing, well, the main takeaway for us is that GR MHD, the combination of GR with fluid dynamics and magnetic fields, actually works. So it had never been tested nearly in such extreme conditions, and you really have to get all the parts moving right, all the equations have to be right, all your assumptions and simplifications have to be right, your coding on the supercomputers has to be right. Sometimes we always get weird bugs that always worry us. If only one bit flips out of computations that take weeks, how wrong would we be? So many things can go wrong. And to see that reality actually matches the predictions of such a complicated model, that gives me a lot of hope that our other predictions are correct too. So we have a lot of models of how more extreme quasars than this works, even brighter supermassive black holes that are eating more and having much more strong jets and much more types of light than just radio. And now I actually have confidence that they're correct, if that makes sense. So it's going to allow us to build models with far less assumptions, far fewer things that we're not quite sure of. We can be, okay, at least the theory, that's correct. This amount of magnetic fields, this amount of rotation, that's what would happen.
Just a small, like very, very small, in fact, not even technically, what's the word? I can't remember the word, but not even a small off-branch. For those who don't know, could you quickly explain what you mean by a bit flip?
By what, sorry?
A bit flip.
Bit flip.
Yes.
A bit flip is the most common type of computer error. that's about as much as I know from it. We have to buy custom GPUs. A lot of the simulations are run on GPUs instead of CPUs that actually have self-correction for bit flips. So they have throughout your calculation, you have to make sure that none of your bits randomly change from a 1 to a 0. It's very unlikely, but if you have billions and billions of calculations, even if it's very unlikely, it will happen eventually. And we have to actually build up all this stuff.
They have extra redundancy, I think, for that.
Yeah, absolutely. So
I mean,
basically, we have a continuous check that if some of the checks turn out wrong, we have to redo the entire calculation because a bit flipped somewhere.
Can't you just flip it back?
No, because you can't know which one. It's awful.
The way that I guess I'll explain it then. The way a bit flip happens, I know this from learning about it when it comes to satellites, but essentially when you get a high energy photon, you'll have heard of the photovoltaic effect, where when you shine light of a high enough energy onto a metal, then it releases electrons. Well, when it comes to a bit flip, it's when light does that and it changes an electrical signal from a 1 to a 0, or from a 0 to a 1, because it can either absorb or it can emit, which is very strange.
Yeah, well, it's a quantum mechanical effect. Every time you have an electron, it can just change state for no reason.
Yeah.
And sometimes if enough electrons do it at once, it can affect your computer cell, or whatever the smallest unit of memory that you're using is. Actually, your hard drive is probably full of them. But unless they pile up, you won't notice.
Even then, the fact that the main worry that, the main area that I know where it's a huge issue is in space, because there's no protection from the atmosphere. for high energy photons. But if you're having to deal with it in a supercomputer with the padding of the atmosphere, that it's so sensitive, or that the calculations are so complex that you still need to worry about them even down here, that is a lot of that. I mean, I don't even know how to put it into words. That is huge amounts of information.
Yep.
That is huge computation.
It's the original butterfly effect. Actually, historically, the first time they noticed the effect was in a simulation of the weather, funnily enough. Because what happened is they had a small computation error. Basically, they had a computer running a weather simulation and it shut down and they had to restore it from memory. But when they restored it, something beyond the sensitivity of the floating point was wrong that they hadn't even recorded, something that was 1 part in a billion billion. And that part in a billion billion was enough to change the entire outcome of the weather prediction. The original butterfly effect. Because even if you start with something small, if your system is extremely chaotic, you never know what knock-on effect it can have. And since then, we have a lot of computer self-checks on things like supercomputers where it matters. It wastes a lot of energy. If only computers were more reliable.
So Kenny has a follow-up question, and he's asking, how do you think Stephen Hawking would have taken this announcement?
He would have tweeted something insightful. No, I'm sure he would have been very happy. He was a great science enthusiast.
Well, in a sense, this well, it doesn't. Does this give us any insight about the Hawking radiation?
No.
No, not at all, right?
No, not even close.
Okay. It's not like some of this light we're seeing comes from that radiation. No, at all.
No.
Okay.
Statistically, not even one photon.
Not even one photon.
In the radio, you'd be hard pressed. And even so, the prediction of Hawking radiation doesn't rely just on general relativity plus fluid mechanics plus magnetic fields. It relies also on Hawking's interpretation of how quantum mechanics plays into it. So it's an early form of quantum relativity, in a way, a very simple form of quantum relativity compared to the full theory that we don't have yet. But that interplay between quantum and relativity is not tested by this image.
And do you think that this way of capturing black holes can't help, even if we get, different targets or more prolonged exposure? It's just...
No, that's not how you would do it if you were trying to test Hawking radiation, because Hawking radiation is one photon once in a while. You're never going to see that one photon at the scale of 1 billion photons that you see in this image, right? The best way to test Hawking radiation would be if Hawking radiation predicts a very specific frequency of photon, like very, very specific. Then you can build a telescope to look only at that frequency and really point in the center of the shadow to see if more of them are coming from there than the outside. Or even look on a very large scale. Look if any of that specific frequency come from it at all, but you don't need high resolution for that.
Would we be able to study Hawking radiation if, by some chance, we created our own black holes, but very, 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 very ridiculously small ones?
Yeah, that would be the best way to actually test it. Because if we have our own black holes, we can make sure they're not feeding. If they're not accreting any gas, then they won't emit any other frequencies of light. They'll just be black and sit there. And then we can really see if they naturally evaporate by sending Hawking radiation.
That's the thing, though, because I mean, if for some reason they didn't actually evaporate due to Hawking radiation, at least not at the rate that we would expect them, then the only outcome of that would be, oh, it's not doing what we thought, and then possibly milliseconds later we're dead. It's just, oh, it's going dead.
That's true. If we are very wrong about how black holes behave, if we are very wrong about how they behave and we try to make one, it could backfire.
Yeah, but
sure.
You would be at least be happy in that millisecond.
Interesting, boom.
Yeah.
I find that very unlikely. Just making a black hole, that's only general relativity. And according to this image, general relativity works quite well. So just making one should be safe. It's not going to blow up or anything.
Okay.
What happens on the very details of the atoms and the photons on the surface, that could be a bit of a disaster. But...
So this, I mean, I'm sorry to go back to it, but I'm still trying to convince my brain that this is actually proof, undeniable proof, that somewhere out there are infinitely small things with infinite density.
Ah, the singularity.
Yeah, I mean, how can you even convince your brain of such a thing?
You shouldn't have to, because there's no evidence of them yet.
Well, there is.
No.
What else can be?
Well, we know how much mass is inside the black hole, and we know that's enough mass to stop light from leaving. That's what we know from the facts. General relativity doesn't attempt to predict things on infinitely small scales. That's the job of quantum mechanics.
No, but...
So actually, scientists don't expect that the singularity is literally infinitely small.
No, but...
Even in theory, it's not infinitely small.
But look, there is something I don't get, okay? Light is massless, okay? The photon has no mass. That's why it can go to the speed of itself, right? Because nothing with mass can reach the speed of light.
Yes.
Which means that light has no mass, being the only thing that can go to the speed of light. Right?
Yes.
Mm-hmm.
Still, gravity, in the case of black holes, does influence light. Which means that for some reason gravity influences even something that has no mass.
It's not gravity that does it, it's the curvature of space-time. The light still thinks it's going straight. If you were the light, you would think you're going straight.
One of the things that I saw quite early on was it was actually a minute physics video where talking about gravity changing, or talking about gravity as in gravity is proportional to mass. The explanation that I saw said that is technically true, but it's better to relate it to momentum and energy. And because light has no momentum because it doesn't have mass, but it does have energy, you can describe gravity like that. But even then, at the levels that we are at, it is better to call it the curvature of space. And it is going in a straight line, it's just that it's not.
As far as we understand, space-time is literally a thing which is literally curved.
Aha.
It's not just a mathematical construct. Space-time has properties. In quantum mechanics, we describe those properties like a density, even.
So, assuming that, well, okay, so we haven't proven that there is an actual singularity.
Currently in physics, a literal singularity as predicted by GR without any part of quantum mechanics. GR predicted should be infinitely small and infinitely dense. That's true. But we know, especially with Hawking's work, that quantum mechanics will mess with you if you get on the scales of an atom or less. So we don't think that the singularity is literally infinite. There's probably some other effect that kicks in. We don't know what. It depends what kind of theory of everything you prefer. But a string in string theory, a string has a minimum size. So then the singularity still has a minimum size.
Well, if you go by like I say orthodox particle theory, you get a quark, which is the smallest thing you can get, right? If you, without going into quantum physics, you have a quark, which is the smallest thing.
A quark is extremely quantum.
Is it?
Yeah, very, very quantum.
Yes.
A quark is...
I thought it was still part of the standard, the...
Particle physics is quantum. Particle physics is very much quantum field theory. They're not separate.
Okay, so is there anything...
Physics.
Is there anything smaller than a quark?
We don't think there's anything that can hold less mass than a quark and still live for very long, apart from neutrinos. They're smaller. Neutrinos are the lightest particles in the standard model. They're so light that we haven't actually measured their mass yet. We just know they have some.
So a black hole could be a quark, just very dense.
I'm not sure if I've just had a very poor explanation of what an axiom is, but what... Or axion. Axiom is an idea. Axion is in standard model. Axion.
Yeah, we're not sure if axions are the answer to what's beyond the standard model. We also know the standard model isn't perfect. It doesn't explain all the behavior of particles.
All right.
Especially when you get to the extremes, like the super small particles in particular, the neutrinos, it gets the most wrong, right?
Okay.
So if a black hole is something the size of a neutrino, the singularity is of that scale, of the smallest physical thing we know of. That's where the standard model is the most wrong already. So
I have a question. The picture does confirm the black hole is spinning, right?
Not entirely constrained, not entirely known. It's hard to tell the difference between. No, okay. So we know we have measured the mass and the spin of the black hole together. Basically, if you have a black hole that's smaller but it spins faster, the exclusion zone around it and the shadow is the same size. So basically, the faster a black hole spins, the bigger its exclusion zone gets. So we know how big the exclusion zone is. If it doesn't spin, we know the mass of the black hole at the center and the size of the event horizon. If it's spinning, that could be smaller and it would still look the same. So we can put some limits on it.
Okay, my reason for the question was I was wondering if this would also confirm the existence of Kerr black holes.
Not necessarily. It could be just a non-spinning black hole. That's possible.
Well, I read an article saying that this is a Kerr black hole.
Most likely, it's a more likely parameter, but it's not completely ruled out that it's not spinning.
Right.
Did they not say that they could tell that it was spinning clockwise, though? Like during the press release, or did I mishear something?
At the very least, the mass around it is being entrained that way. We don't know how much, or if the mass is just moving that way, even though the black hole isn't. I don't think it's entirely decided yet, although I may be wrong. It may be somewhere in the papers. I haven't read all of the 8 papers entirely yet.
Okay.
Well, I will. You bet I will.
I wish I could, but I don't have the knowledge for it. Not yet.
What's clicking?
That's me just playing, just trying to get a good screenshot on my planet I just found. Ignore me! Anyway, we got another question.
Yes.
From YouTube, right?
It's not a real question, it's a comment.
Yeah, I know, it's not really a question, yeah.
No, actually, I had this debate with a colleague today.
What?
Believe it or not, that's.
Maybe this is your colleague.
No, it's a pedantic question.
Don't insult our listeners.
No, pedantic isn't a bad word. It's good to be accurate. Pedantic is good. I'm very pedantic in my reviews of other papers.
Yeah, I know you are.
Me too.
Okay.
Right. Really, what it comes down to is, what do you call a black hole?
Okay, so let me just read the question. Okay. So it's this Loot. I'm not sure how to pronounce his name.
Loot.
Anyway, although the new photo is great, we will never ever see a black hole, not even with Hawking radiation. I'm not sure what this means, because the picture is a literal black hole.
It depends what you define a black hole to be. And that's something that even astrophysicists argue between themselves about. It's a question of wording and specific definitions, right? So is the black hole just a singularity? Technically, that's where the hole is. It's a hole in space-time where it gets infinitely curved, so it's basically torn. It's a hole in space-time called a black hole. That's where the word comes from in GR. So is that the black hole, the singularity, which you can never see because it's hidden? Or is the black hole really a structure comprising of a singularity and its effects, including the event horizon?
Well,
because if the black hole is the entire structure, then we are seeing it because we're seeing the outside of the structure, which is the event horizon, but the black hole is the whole thing. That's why I said it's very pedantic. It depends how you define it.
Then where another thing would be, where would you include the ergosphere?
That's inside the event horizon. It's part of the structure, one of the parts you can never see.
Ah.
You will only ever see the event horizon.
Well, as far as I know, there would be no point in having the black hole being the singularity, because you have already a term, singularity, to define that.
Yeah, and the event horizon is called the event horizon.
Yeah, exactly. But the entire thing, the event horizon is just the line. Okay, it is the boundary. That either it's a line. Okay, you are either on one side of the event horizon or you are on the other side. The singularity is the point at the center of the sphere, and the black hole is the entire black sphere in itself, which is composed by the singularity at the center and the area that is delimited by the event horizon. So this is where
I have an advantage, being in high school and pedantic, because I know what my exact definition has been given based off of my course material.
But careful, high school courses are often wrong.
Yes,
my
I know, but I'm a smart ass.
So anyway. I only realized when I actually went to do physics at uni how often my physics teachers had been wrong in high school.
Yeah.
Did you go back and tell them, being pedantic?
Actually, I did.
Well, anyway, the official definition, according to my coursework, is the event horizon is the point at which nothing can. Oh no, I've forgotten. Oh my god.
You really suck at talking,
Oh,
yeah, I do.
Rude.
I do. No, I do. I need to. One of these days I'm gonna learn to speak my own language.
Yeah, that would be a start.
I went into this hoping that I could actually give a valid point to the conversation, but then when I actually
I get what you said. It's defined as the point beyond which not even light can escape. The question is it part of a structure called the black hole, or is it just separate? It doesn't matter. It's just a matter of definitions.
That's the thing. I was thinking of the Schwarzschild radius. Schwarzschild radius is defined as the radius between, or the distance between, the singularity of a black hole and the event and the edge of the event horizon. But I don't actually have a definition of a singularity or an event horizon. So
I don't know, but what you're saying is still consistent to what I said. You have the singularity, which is this thing at the center. You have the event horizon, which is basically imagine a hot air balloon. You have the membrane, which keeps the black hole inside, and that's just the circumference of a sphere, okay, the surface of the sphere, which is the event horizon. Then you have the actual black hole, which is the entire structure. You have the singularity, you have the event horizon, and everything in between.
And depending on how you want to use the word, all the structure outside of it can also be called the black hole.
No, then you have the accretion disk. You have
but
yes.
In my work, in my day-to-day work, right? If I observe a galaxy and I ask, I wonder what the black hole in the center is doing, I mean the entire structure that is related to the black hole. So including the accretion disk and the torus and the jets. What's the black hole doing?
I understand.
To a bigger scale.
It depends on the context. I believe that this comment from Loot is talking about a singularity. We will never see a naked singularity.
No.
That's
I'd like to add, we've got a bit more information from Captain Comeback, saying that the event horizon is the point at which information cannot be observed. But by that definition, would the event horizon then not include the silhouette of the black hole? But we define them as two different. Or how so?
One of the reasons we don't see matter in the excluded zone is that it doesn't stay there very long, but it's still technically there, and you can still technically see it. If the light is pointing just right, so it's not theoretically forbidden, just practically forbidden.
Oh, okay.
Let me take some quick questions from
indeed.
the stream.
I was
so
going
Commander
to...
Acerino
Acerino
asks, Acerino, it sounds Italian, asks, I may have missed something, are we looking at the black hole from its pole or edge on? So based on which parts of it are brighter, as we mentioned earlier, we're looking at it at an angle compared to the disk of the gas between 18 and 30 degrees. So not edge on and not face on, kind of in between. And then Akorlei asks, have we determined if the black hole is literally a hole having a flat plane and then a hole in the center, or is the black hole more like a sphere? The event horizon that we can see in this image is definitely a sphere. It's just the gas around it prefers to settle into a small plane or a small disk around the sphere, kind of like rings around the planet.
Why is that? Is that just a natural trend, or is it just coincidence? Because I mean, surely it should technically be possible for it to be a bubble.
No, it tends not to, basically because of friction and conservation of angular momentum. So imagine that some gas is falling on this disk from the wrong angle. It's not aligned. Well, every time it passes through the disk, it will lose a bit of angular momentum because that's where the rest of the gas is. It slows down a bit every time it crosses this preferred plane. So over many times, it will always lose a bit of speed at that point when it's spinning around. So it will line up more and more over time until the friction forces it into the same plane as the rest.
Oh, okay.
So it's kind of self-perpetuating. When you have a disk, it stays a disk.
And so is that why the accretion disk doesn't necessarily have to be on the same plane as the galaxy itself? Like, just in general, because of the fact that the prevailing... what did I just say? The prevailing...
Orientation
or inclination doesn't necessarily have anything to do with the galactic.
So definitely. Okay. So say this black hole was dormant for a while. It finishes eating, and then one day a star falls in. Well, it can fall in and miss from any orientation or any angle, but the angle it misses on will become the new inner disk, basically. And then if the black hole itself is already spinning in a different direction, you can get a strange misalignment, and then the disk gets kind of distorted, and it looks pretty cool. But as a general rule, it can face any direction. It's just random. Sometimes we even see quasars that have jets, and the jets actually go into their host galaxy, like in the plane of the galaxy where the stars are. That's where the jets go, instead of going up and down.
That sounds dangerous.
Yeah, it's pretty awesome.
So no life in that galaxy?
Not on the path of the jets, definitely not. Actually, there's a whole field of research about how exactly how deadly quasars can be to their hosts. Actually, the latest results for Sagae, or the last time Sagae was active, everything up to 1/4 of the way to the Earth was sterilized. The amount of X-rays that were emitted up to 1/4 of the way to the Earth was for sure dead. That's pretty bad. Might be why we don't see, for example, more
people
life. Maybe why we don't see life at the center of the galaxy, even though that's where all the old stars are. But if they get sterilized every 2 or 3 billion years, they wouldn't have the time to evolve like we did. So maybe being far away from the center is actually a good thing for life.
I guess we have a Goldilocks zone on a galaxy scale.
Pretty much.
Yeah, we have quite a few questions appearing now.
Oh, also a quick tangent before you ask the next question. I think we should make it a tangent. We should make it a running gag of mispronouncing Akorlai's name on the streams.
Yeah,
it's Akorlai.
Oh, I'm so sorry.
What did you call it?
Probably not that.
You said a collie, lay, lure. I don't. It's not. It's not.
I'm going to call him Acrelay.
Asorley.
Yeah.
Adam.
Well, anyway,
my joke was poor. I apologize.
So,
That's fine.
yeah, Captain Comeback asked a few questions, but I believe we answered them during our chatting.
No, some of them are really good questions, as I say.
Yeah, no, I was just scrolling up. He's asking, now that we can see the presumable rotation of the black hole and the accretion disk, is this telling us anything new about star formation in galaxies in regard to their central supermassive black holes?
Yeah, okay. That's a good one. That's one of the things I actually work on. So to what extent can a black hole, supermassive, active at the center of a galaxy, how much can that affect star formation on the entire galaxy scale? Well, the most direct result of this image is that we trust our models of what goes on in the inner regions now. So this is a pretty inactive black hole compared to the ones we study that are currently affecting the entire galaxy. But because our models worked well in this case, now we trust the models in the more extreme cases too. So it's indirect. This particular black hole was probably a lot more active in the past. For example, we mentioned it's in an elliptical galaxy, and elliptical galaxies tend to be formed by the merger of many spiral galaxies until you don't have a recognizable disk anymore. And those also had the biggest black holes and the most active quasars. I think they peaked around 6 billion years ago. 6 billion years ago is when the average elliptical galaxy was super active because all this gas from the collisions was being funneled into the center at super high rates, and quasars really had their golden age about 6 billion years ago. They were all a lot brighter than they are today. And at that time, they would have killed a lot of the star formation in elliptical galaxies like this one. So one of the reasons it looks like it does and it stopped making new stars, part of that, we think, is because the quasar killed it at its peak. No more new stars for this galaxy.
So, because this, I mean, M87, the way we are seeing it is, what, 55 million years old. As far as, I mean, we are seeing this black hole as it looked like 55 million years old, years ago, yeah. Right? And so when you say that you believe that M87 was more active in the past, you mean even before that?
Much before. So the peak of quasars in the universe was 6 billion years ago. Billion. And this one we're seeing as it was 55 million years ago.
Yeah, but I assume that M87 wasn't around. I mean, sorry, can you repeat that? I may have misheard.
So the peak of activity in elliptical galaxies like this one, on average in the universe.
But not this specific one.
No, on average. So the universe had phases, right? We know this from the galaxies that are really far away. We know that 6 billion years ago, there was a big phase of intense quasar activity.
So we don't know how old the M87 is.
Whoa. I must have misheard. Did you say 66 billion?
6 billion.
Oh, 6 but right.
6 billion years ago was the peak of quasars.
Sorry, that's my hearing.
Likely including this one. I mean, this one we only see as it was 55 million years ago. But on average, the universe had a phase. It was just a phase.
Do you think there is a chance to see, because of course you work on distant quasars, and this is quite close to us, I guess.
Yep.
Is there a chance to, I mean, probably the answer is no, but what are the chances of getting such images from something really, really far?
So we need bigger baselines. We need to go to space if you want to do something like that. We need telescopes more far away from each other than the size of the Earth.
Couldn't we include Hubble? Or the James Webb Telescope when it's up?
No.
It does not see radio. Actually, only two space telescopes see radio. we could use those, although that's still not a big increase. If you want to see 10 times smaller things, you need a size of your telescope 10 times bigger than the Earth. So you need like many small telescopes in space just floating around.
Even then, the average, if I've been told correctly, the standard or calibration uncertainty would be related to the average distance between all of the different telescopes, would it not?
So you would yeah, but even in this case, they don't do that on the fly. So they actually record the data. For the Event Horizon Telescope, they recorded each data for each telescope separately on big disks of storage. And then they physically shipped the recorded disks all to the same location. And they had to work out after the fact the exact precise timing difference. So it's not like they did it in real time. Using clever quantum mechanical tricks and storage tricks, they were able to do that, what we call the correlation of the different signals. They could do that later. So we can do it in space too, same principle. Download them all to the Earth and then process it here.
Sorry, I'm looking at a post that one of our listeners, Zalva, posted on the channel. I'm not sure what I'm looking at here.
So
it's a post by NASA.
Yeah, and it was in one of the press conferences too. So it's a picture from a different telescope of the same center of this galaxy, but on a bigger scale, I think.
Oh, wow.
So that's what I meant.
I struggle to see from that post, but it looks like the one they showed in the press conference.
Well, the post is mentioning that. So I guess.
I'm trying to find the source of it.
It says Chandra X-ray.
Oh yeah, I can see a few examples online. Yeah, so it's images taken by other telescopes of the bigger area around it, for which you don't need many telescopes. You can just do it with one.
Yeah, that's just the galaxy, right?
It's the galaxy, but you can see stuff is happening.
Yeah, obviously.
So there's a jet coming out there, which is not actually lined up. If you look carefully at that image, the jet that goes all the way to the right doesn't seem to be aligned with the jet coming out from the central region. So that suggests the black hole is actually precessing. The entire structure of the black hole plus the jet is spinning through space.
Huh.
Which is a thing that happens quite often. So using this, we can really work out where the jet is coming from, how fast it's moving, how fast the black hole is moving. The really exciting thing is linking the very inner region, that now we finally know what the inner regions are, to all these extra processes on the outskirts, all the way outside of the galaxy.
Quite wild.
Quite wild. It is quite wild.
Do you want to answer any other questions? Because you mentioned that you've seen some interesting ones.
Let me just post this.
I believe there was another one from Ikro Lee. I believe that's how it's pronounced. Correct me if I am mistaken. So Ikro Lee was asking if he says that he's rather reaching with this question, since we are in our infancy, especially Selfish Pie.
Hello.
And he is asking, having observed the black hole now, do you believe, in all honesty, that this will have any effect or implication on space travel? Will there be any more push to continue to explore the stars?
Probably not directly.
Well,
the thing with this image is that it really matched very closely, at least some of the simulations that we made. It's not like we knew exactly what it was going to look like. We had a big range of simulations, hundreds, depending on how big the disk is, how puffy the disk is, how strong the magnetic fields are. But one of these models, or at least one, actually matched very closely to what we saw. So that means that basically physics is right. We didn't learn any new physics. It means all the physics that went into the prediction were actually correct. And sometimes in science, you just confirm what you already know. Actually, I was watching the stream of the conference, the US one, and I read some AMA that they got later. It's really funny to me how some of the members of the Event Horizon Telescope actually sound kind of disappointed that it matched so well. They were like, oh, but it could have been a bit more squished. It would have been a bit more asymmetric. Maybe GR was going to be wrong. And then we'd have a new theory.
Everyone wants to disprove Einstein, right? They would be famous.
Well, it would be more exciting.
The people who disproven Einstein, right?
It would be good to have a hint of what the theory of everything actually is. We know GR doesn't work always. We know quantum mechanics doesn't work always. So the more hints we can see of how it fails, the quicker we'll get at the unified
But isn't
theory.
it the same thing? I mean, you're getting hints on how it succeeds. That's even better,
but we already know the theory that succeeds. It just works so
yeah, but you have
well.
confirmed it now. That's part of science, right? You need to confirm things.
It's okay. We have to test things. So whether it agrees or it doesn't agree, you have to look at what is.
Yeah, and this was a test.
But from a personal point of view, it's more exciting if it doesn't agree. Then there's more work to do.
And yes. I guess you don't risk getting fired, but
there's more space for me to be famous.
Yeah, I guess. I mean, I get what you're saying, but so this doesn't really help us to on a grand scale to realize. Because, okay, you just mentioned that we know that GR fails.
It doesn't help us solve physics.
Exactly. I mean, we know that GR fails in some cases. So the fact that we have now confirmed that Einstein was right doesn't mean that he was right, like, in all accounts.
But it makes our life harder. Because say you want to come up with an alternative theory of gravity. Say you think fairies did it, whatever. So you want to find the one thing that GR can't do, and you want to explain it with your exotic theory. Now, it's all well and good that your theory can do the thing that GR cannot, but if your fairy theory fails on all the other things that do work, it's probably not right. So you have to also match all the regimes in which GR is right, in addition to the part where GR is wrong, which is where a lot of alternative theories of gravity fail. They cannot do as well as GR in the past it does well, even if they can explain some things that GR can't. And this test was the most high extreme test of GR, the most curvature of space-time we've ever imaged, more than any lab, more than anything in our solar system, more than any timing of GPS accuracy on the surface of the Earth. It was a test of GR in the most extreme space-time environment ever. We were hoping that's where it would fail. Well, hoping. Maybe if you pushed it to this limit, it would start to show some cracks, but it didn't. And now all other theories of gravity, like string theory, have to function in this extreme circumstance too.
Yeah, but isn't that good? You're restricting the possibilities that, I mean, you are what I'm hearing. Maybe I'm wrong, but is that having confirmed this, then we can rule out a lot of other things. So we are actually getting closer to truth because we are just, okay, guys, you know that theory that was promising, it doesn't really work because now we have proof that it doesn't. That
would be true if we had even one that actually worked in all cases, but we don't.
Well, that's your problem. Get to work. Yeah, instead of being here talking and not doing your job.
Oh, I feel so appreciated.
Yeah, well,
that's what my boss thinks too.
Yeah, I mean, your boss is right.
Work more, yes, of course.
Yeah, work more, earn your money.
Well, you know how many hours I work a day? Too many.
All I'm saying is, the way I see it, again, maybe I'm naive, I'm not a scientist, I'm commenting this from the outside, but anything that gets us closer to the truth is good. And
I think so,
if this discovery helps us to rule out things, I feel sorry for whoever scientist was behind those theories, but that's how science works. Not everyone can be right.
Of course, testing everything is good. Always having more information, more constraints, more tests. And in this case, it's a very cool test. Yeah. So that helps. I think in terms of space exploration, the best thing this can do is build enthusiasm about space.
And that is very good for me.
Yes,
I have heard.
Get a job. There will be funding.
Yes,
I have heard people saying that the scientists on the panel didn't do a good job to to bring this to the public. What do you think?
I think they did an okay job. Actually, that's the topic that my colleagues and I discussed the most.
They did.
After the press conference, we're debating what they did wrong, what they could have done better in terms of outreach, not in terms of science, because we knew the science. The way they presented it was interesting.
They should have invited, like, I don't know, Tyson to present it or something.
Neil deGrasse Tyson.
Yeah, just to do the presentation, you know, just to have the charisma and the media appeal.
Well, they didn't prepare any.
Because in the end, it was just a bunch of nerds saying things in a very awkward way. So
they didn't prepare any easy to understand graphics. Like, if any of you remember the LIGO announcement, they had like even this cute video for kids about your gravitational wave, it travels through space and then we see it.
Yeah,
it was like really cheerful.
There was really a disturbing lack of PowerPoint slides.
I mean,
which is the staple of science. PowerPoint. You need to have PowerPoint.
No, there was a bit of PowerPoint, but they didn't prepare any outreach, immediate media material. I mean,
they had 2 years. Come on.
But they could have, for example, given the newspapers the picture one day in advance, like LIGO did. Actually, LIGO sent.
It would have leaked. Like
no, LIGO did it. That's what we call an embargo in media. You send something to a newspaper saying, publish this tomorrow. Until tomorrow, there's an embargo. If they break it, they can be fined enormously. So they don't do it. Okay, they don't do it. It's a thing that scientists do quite often. But in this case, for whatever reason, they didn't do that. They didn't send the picture to anyone in advance. Even the outreach departments of their own institutions would prepare all these cute graphics. Like, this black hole is this amount of masses. It's as much as X times the sun, and then like big numbers and happy figures. But they didn't do that this time.
I guess they were really, really
busy.
Secretive.
Very secretive. Extremely secretive.
Yeah. But
probably a bit too much.
I don't know. I mean, such a thing is they called it the photograph of the century.
Yeah.
So I want to make a comment about that, but first let me just check if we have.
Well, it is the picture that will end up in textbooks for years to come.
Yeah.
There'll be more, but this will obviously be the first one. And
it competes with the ALMA detection from a few years ago, the first protoplanetary disk, the first birth of a solar system seen live, which used the same technique, by the way. That's the other competitor for an astronomy picture of the century, in my mind.
So, Tor, let's take some...
Yeah?
I'm going to be honest, I forgot that was a thing.
I was speechless when I saw that.
We have only about 20-25 minutes left. Let me take just a few more questions because we left a few behind.
Right, let's do them quick.
Tornado Pelt was asking what would happen if a tablespoon of those relativistic gases was slammed into Earth.
You would.
I mean, that's just gas, right? It's not neutron star material. It's just gas.
Fast.
It's fast, but
a teaspoon, it wouldn't be that dense, but it would still destroy the atmosphere to some extent. It wouldn't destroy the Earth, but you would get at the very least extremely strong. What are they called? Aurora borealis, whatever the common word for that is. You know, the things you see with lights in the sky and the poles.
Southern lights.
Yeah. Northern and southern lights. You see them on steroids from all the ionized particles hitting the atmosphere. The sky would light up.
They wouldn't really reach the ground, though.
They might destroy the atmosphere in the process.
Just a tablespoon.
Yeah. It would be enough to blow a small hole in the atmosphere. And then it would probably close itself, but not immediately. So for a while, it would have something like a hole in the ozone layer. And would be in a bit of danger, but I don't think it would destroy the Earth. I think most of the atmosphere will just stay.
Well, I mean, human beings were stupid. People would probably end up saying, "Oh, it's a hoax. Let's ignore it," or something.
Well, if you could see the night sky light up in a billion colors and the light of the sun.
So what if there is a hole in the sky? Let's build a wall and close it. That's pretty much what would happen, right?
Yeah. Let's build an iron bubble around the Earth.
Yeah, so no sunlight gets ever back in.
Yeah.
Let's build a Dyson sphere, but the twist is around the Earth.
You have to keep these immigrant particles out.
Yeah, just so no, I was going to. I mean, did you see any other interesting question that you wanted to answer, or?
I think we've gone through most of them.
So I'm going to read out the comment.
That Michael says Professor Cathy Bauman was the person responsible for taking the picture of the black hole.
It wasn't me. It was. Oh God, I can't read the name.
Image1. Image1.
Yeah.
Partially true. Not fair.
She's the computer scientist behind the calculations, or at least she presented it.
Fair. It is not fair because as the American press conference did a great job of that. My PhD student wouldn't stop laughing when they did that. They were showing the different stages of going from the data to the picture, right? So collection, and then there was the correlation, and then there was the part where you reduce the data to remove all the contaminants before you do the imaging. And he said that was most of the work, and it was done mostly by early career postdocs and PhD students. That is very true.
They mentioned that.
Yeah, they mentioned that because in academia, those people do 90% of the work. They don't design studies. They don't get to steer where the science goes. But the actual sitting down, running stuff for 20 hours a day in a basement, we do it. The early career researchers and the PhD students, and at least for once they were acknowledged because people aren't aware of this. They get 0% of the recognition, and yet they are the biggest part of the workforce by far.
Don't they still appear on papers?
They do, but most of them don't get careers. So the success rate from getting a PhD to becoming a professor is less than 10%. Most of them never get a career in a university. Oof. So they are the unspoken slave workforce. That's the stereotype that they see themselves at. It's not completely wrong.
Well, I guess there must be a way to get to the top, though, right?
It's a way for them to learn the method, too. The truth is, it takes them more time than it would if a professor did it. But they have to learn. Also, they need to acquire enough knowledge to know what to plan next. When they get to the planning stage, what telescope to build next, and so on. The people there need to have a lot of accumulated experience. But by that point, you're almost a manager. You decide what science will do next, and then you give the tasks to other people.
Okay.
This is why I just want to be the director of a planetarium.
Well, you don't... That's why I want to be a professor. I feel like it's actually less work. It's less like grueling reductions, looking at blurry images for 10 hours a day. Just 2 weeks ago.
This specific blurry image is good, though, right?
Just 2 weeks ago, right, I became an expert in reducing data from a telescope that doesn't even exist anymore. That took me 3 weeks because I wanted to make sure that some image from a paper was actually done correctly by the people who did it 15 years ago.
And was it?
No, it was not. It was slightly wrong, and I actually really cared about the ways it was slightly wrong.
And you should be happy, right?
Because now I'm an expert in outdated Fortran, deprecated Bash scripts, and a telescope which hasn't existed for 10 years. So, yay for me. No professor would sit down and do that for 3 weeks. Let me tell you that.
But it's a story you can tell your grandkids.
It's something I can put on my CV under useless skills. Did you know that Bash syntax actually changed? And quotation marks used to mean something different. No one does that. No one cares. But it still took me 2 days to work it out. Anyway, that was private rant.
I guess you had a lot of free time, huh?
It's my job.
Fair.
It sounds like free time, but it's actually my job.
So other people who wrote that paper are actually still alive?
Yeah, no, they are.
Okay.
And they actually warned us that the pictures weren't entirely accurate. So
they knew.
They were taken for a different purpose and needed much higher accuracy. So
right.
Anyway. So Image1 points out that Professor Cathy Bauman gave a talk on how to take a picture of a black hole in 2007. That's true. But she didn't invent the technique. Interferometry has been around for much, much longer, pretty much as long as radio telescopes have been around. The Event Horizon Telescope refined it and organized the cooperation to push the technique to its limits, the limit of the size of the Earth.
Also,
you cannot credit one person for coming up with it. That's not fair.
Isn't there also laser interferometry, which is being used to reduce atmospheric distortions from Earth-based telescopes?
Yeah, there's that too. I don't think this particular observation used it. But yeah, interferometry has been used for a lot of different purposes. Even this specific type of radio interferometry is actually quite old. What the Event Horizon Telescope did was really push it to its limits. Conceptually, it's not that new. In terms of a technological prowess, it's amazing. And the actual grueling groundwork was done mostly by uncredited PhD students and early career researchers. All props to them. They will not get the Nobel Prize or even their name first on their paper, but they did most of it.
It's good. It's good to hear that, because of course you've been one of them, right? Before you climbed the ranks.
I think I still am. I'm still early career by most.
Yeah, no, but you're not a student.
No.
You may still early career, but you're young, and your track record shows that you'll be climbing out of that hole, if you want to call it like that, eventually, hopefully quite fast. But it's good to tell. I don't know if among our listeners there's people who are planning to to
make a career
follow
in science.
That career. Yeah, and that is encouraging. And in a sense, because
it's also kind of fair.
Yeah, I know selfish you are.
Yes. By the way, my previous joke was in reference to Neil deGrasse Tyson. He's the professor of astrophysics. You know what I mean. Hopefully.
You know who he is.
But my joke was poor. A lot of my jokes are poor.
What did I tell you last time? You need to write the jokes down if you can't remember them.
Well, no, it's not that I couldn't remember it. It's that I just have poor jokes. I am not a comedian.
But that's good, because scientists are bad at jokes, so you're on the right track there.
Yeah.
Well,
yeah.
You can put that on your CV. Bad at jokes. You'll be hired by any uni.
Nah.
To finish on this topic, Image1 points out that the press isn't mentioning Professor Cathy Bauman. I don't think the press should mention any particular professor in particular. I think that's not fair. All of the papers, if you look at the author list, it's not in the name of any of them. It's the collaboration. It's the collaborations paper. And if you were going by number of hours put in, the number one would not be a professor. I am almost completely sure of that.
So would
just because of the way things tend to work.
Some underpaid students.
Even if you went by who did the most management, that might be fair. Who did the most planning? There's many ways to determine who should be credited first. And they don't try to do that. They don't kill each other. It's a collaborative effort. And we should just credit the collaboration. If the media is trying to single out a single person, I think that's wrong.
Exactly.
Yeah, that's the thing. Because the days of Einstein's and maybe even Hawking's may be long past.
No.
Don't let me just expand to that. Of course, you will still have people of relevance that are more popular with the media. Again, we mentioned Tyson. There's other scientists that are more, that they have a public face. But I believe that you mentioned in a few cases that one thing is, I mean, like Tyson is or even Carl Sagan, they weren't really doing research as you or other colleagues do. They are extremely good at what they do, and that is bringing science to the public to make them understand what actually happens. But people who actually crunch the numbers and discover new things are busy doing that rather than going on
yes
TV
no.
or.
It's true that nowadays the most public figures like Tyson, Brian Cox, Chris Lintott, and so on spend a lot more time doing outreach and actual research. That's always been true. There's always been dedicated outreachers. That's not what Einstein was. Einstein came up with a new theory, and he was not particularly good at speaking.
Obviously, he was not an outreacher. Clearly, that's not what I was implying. I apologize if.
It's also true that science is more collaborative these days, but observational science has always been collaborative and unrewarded by the public. I'm going to say that. Everyone knows Einstein, right? Everyone knows he came up with GR. But who came up with radio telescopes? Who came up with the first proof of GR? People don't even know their names unless you're a scientist. The greatest observationalists of all time, including my idol, Sir Arthur Eddington, the public doesn't even know who he is. Yet in terms of scientific impact on how we view the universe, he is up there with Einstein. He came up with observational techniques, he put in the hours, found ways to actually observe and test science. But the public doesn't care about that. That's not sexy. No one knows the names of telescope builders, lab scientists. The public likes idols that have ideas. So someone like Einstein, huge public figure, came up with GR. Stephen Hawking, huge public figure. Of course, he was good at writing, but he came up with very abstract, difficult theories. That's impressive. The media cares. People like that we still have. Physics still has its superstars that are coming up with the best theories of string theory, M theory, very highly theoretical stuff. I think the most famous physicist currently is Maldacena. He's a theoretical physicist that came up with the ADS-CFT correspondence, which is the biggest physical progress in theory of the last 30 years easily. People don't know his name because he doesn't write books and he's not particularly, charismatic. But science is still driven by people like him who have a great idea once in a while. In terms of theory, though, and those are the people that tend to get the attention. Big projects that were milestones in observation, like LIGO or this picture, were A, always a collaboration, and B, no one ever knew the names of the people who did them. No one knows who took the first picture of a galaxy outside of our Milky Way. No one knows who proved that galaxies were far away using hours of observations. It was Hubble. You've heard the name Hubble. That's what he did. He proved how far away other galaxies are from us. But before Hubble, lots of people thought galaxies were just clouds in our own galaxy, and they were wrong. He showed that there were galaxies outside the Milky Way. But people don't remember that. It's not sexy enough. That's also my private rant as an observer.
Yeah, you can call it a rant. It is quite interesting, to be fair, because you mentioned Hubble, and I believe that most people know the name because of the telescope rather than the person behind it. You know the Hubble telescope, but it's many people know the first name of Einstein. Okay.
Well,
you know that Einstein is Albert Einstein, but I don't know how many people know the actual first name of Hubble. Just know the Hubble
Edwin Hubble.
Yeah, no, okay, fine, but I think most people wouldn't know because they know the name from the telescope.
And yet, I think he changed our view of the universe just as much as Einstein did.
Even then, people probably know of the Hubble telescope, people probably know of the Hubble telescope because of the fact that it was originally this huge, fantastic project that in the beginning it failed because of the error with the mirror, and people attached to that, it's another one of NASA's failings, because that was the view at the time. But arguably it still is, obviously to less of an extent, otherwise we wouldn't have SpaceX doing as well as they are and all of that other such stuff. There is growth now, but a lot of people, they attach a disrespect towards it rather than, that's a strange name, I've not heard that, where's it come from? Nowadays they would do that, and especially, in my school we've got these signs up on the wall and it's like quotes from people, and one of them is from Edwin Hubble, where it's science is the I can't remember exactly what it is, but it's essentially scientists use to look at the universe. Universe supplies senses or something like that. Actually, the only reason.
You read the quote for next week, and then you can tell us properly, okay?
Yeah.
I didn't mean to offend you, Selfish. Sorry.
No, it's.
Don't cry. It's fine. It's don't. I didn't mean to.
It's fine.
Don't cry.
Well,
sorry.
anyway. Essentially, what I'm saying is, the only reason that I knew his first name was because it was on the wall of our school. I mean, I would have eventually went and looked into it because I was obviously I love all of this sort of stuff. I'm curious. I love the history of space, but there is ultimately an attitude that has developed in the public that needs to, not necessarily needs to change, but it needs to be shown a new perspective. And if people decide, oh, I like that one, I'm going to leave this one behind because it was ultimately disrespectful, in a sense, then that's going to be when there's a shift. But we don't have that yet.
What Shoba is saying is that the media, and by extent the people who consume the media, are more fascinated by individuals like Einstein that have brilliant ideas, and they tend to kind of put on the background the actual technical geniuses that make those things actually happen.
Exactly.
We take it for granted. We think anyone could go and look, right? Except we haven't just looked at things for a long time.
Maybe I'm just reaching too far, but it feels like, in a world that is very dominated by technology, we have technology at our fingertips. It feels like trivial, the hard thing is to have the idea, to have the theory, to have the equation, to have the math. Then technology is just there. You just need someone to point the finger, and then technology will just build something very quickly to look where the finger is pointing. But the important thing is the brain of the person who is pointing the finger. Technology is just, oh, of course that's the target. Why couldn't we think about that before? That's easy. Let's just build this extremely expensive telescope.
Which will magically work, right?
It doesn't. It's not as poetic as the person who has the spark of genius.
Exactly.
And so I understand what you're saying. It is not fair. It is indeed not fair. And especially since
people love to put people don't like seemingly empty explanations. If I've put that correctly, they like faces. They like personalizations. And so when you hear relativity, you immediately think, oh, Einstein. He was a genius. He did that.
You think you hear black holes, you think Hawking.
Yeah. When you hear
I still think Einstein with black holes, but that's just me, I guess.
You're correct.
We do that, but like in the eye of someone who, oh well, I'm just going to say something arbitrary, just as an example. A hairdresser, like why would a hairdresser know that Einstein did a lot on, or well, not a lot, but like he did stuff on black holes? That's sort of where it begins to appear itself. What do people associate with the idea? When it comes to the expansion of the universe, sure, people who have a sort of deeper knowledge will go, oh, I think, what was it, Hubble? But whenever it comes to stuff like the expansion of the universe, they'll attribute it to other ideas, like, oh, I heard about that, dark energy. well, what's dark energy? And then eventually, or well, in this specific example, someone will say, oh, we don't know. And people don't like that.
Yeah, no. I mean, it's
at what
of course,
point
and then,
do you get a person in front of your face?
Yeah, and then religion happens, but that's besides the point.
No. Then people assume that people like Neil deGrasse Tyson did all of astronomy.
Right.
Which is definitely not the case.
Yeah, I mean, it's not like everyone needs to know everything, because we have experts like you for that. And I am grateful. I'm grateful to outreachers like Neil deGrasse and of course Carl Sagan, because they help in their own way. They do what they do best. Science is, especially when we reach these extremes of what we know and what we don't know, science can get pretty hard, and not everyone can get it. Otherwise, everyone would be a scientist. So we need people that bring things down. At the same time, I agree that we should recognize a bit more whoever is crunching the numbers. But sadly, media's like their headlines and their faces, and that it's a bit of a paradox, because what this result we got today came from a collaboration of different, 8 telescopes from all over the place, working together.
20 universities.
There is no single face. You have a bunch of faces. And what Shaba was saying before, they did the right thing, I believe, not to mention specific names or a single specific name. I think it was a deliberate choice. They want to make it clear that without the collective effort, this would not be possible. Sadly, this is maybe not easily marketable as a new Einstein. But that's how science is going to go, because it's getting more expensive than ever was. We require bigger structures. We require a lot of different experts in fluids, in dynamics, in quantum physics, and it's getting harder and harder. And we need to pool all of our brains. And sometimes I guess we need to leave ego aside, right?
Right.
For science, you always have to.
Unless you're going insane and trying to be like Linus Pauling.
No.
Anyway, do we have any other question? Otherwise, I'm going to ask something cheeky myself.
Go on.
Ooh.
Because we are out of time, so I wanted to conclude with a divisive question.
Ooh.
So, this has been called the picture of the century. Now, there was another picture that time ago was labeled as such. And, of course, it is the famous picture of the eclipse that Einstein used in 1919 to... Let me finish.
No.
Another century.
No. It was not Einstein.
Well, okay.
That was my whole point. It was Sir Arthur Eddington.
Okay, sure. Okay, that's Sir Arthur Eddington.
Thank you.
Took
Division chief
to prove that Einstein's theory was indeed correct, and it did prove that light from distant stars was being bent by the gravity of the sun, right?
Yeah.
And there was a picture that was very famous at the time, and I believe it was in May of 1919, pretty much 100 years ago.
Yeah.
This was mentioned in a few articles. Of course, the name of your idol was not mentioned.
Completely for no reason.
It was only Einstein was mentioned. It was, for the exact same reason we just talked about. And it was pretty much 100 years ago. Now, is it a coincidence that exactly 100 years later, a new picture of the century comes out, proving that Einstein was again correct on the same theory that that old picture 100 years ago started to prove.
Yeah, it is. I mean, LIGO also
that's a boring answer. I was expecting
a few years ago, and this picture was actually taken in April of 2017.
Exactly. So that's my point. Do you think that whoever is, this collaboration waited for today just because of that?
No, then they would have waited for May 29th.
No, they couldn't make it too obvious.
I don't think so.
Yeah, either obvious or not at all.
No. If it was exactly on the same day, that would have been without question. Yeah. Now we are just a bit more than 1 month, but it's still exactly 100 years after.
Is there a conspiracy?
Exactly.
Human beings have, and you'll have heard this, but human beings have a natural disposition towards looking for patterns and seeing them where they aren't. That's the only reason people think that coincidences don't actually happen.
Of course, it is a provocation. Okay,
Twist.
I will just want, because I'm sure someone will come up with that.
Twist. There is this enormous funding round called Astronomy 2020. For which the deadline for applying for extra funding is, I think, this summer. Were they trying to get it out before the deadline for the next 20 years of funding? Maybe. Maybe they hurried to get it out in time. Maybe they were waiting to have Sagae too and publish both black holes at once, but then they thought, we might not have Sagae in time.
They did. I'm pretty sure Veritasium. He has a video out today, just after. I think I've not watched it because it released it during the broadcast here.
No, it was released yesterday.
No. There was one released today.
Oh. Okay.
That had a picture of M87 and Sagae in the thumbnail.
I don't think they released Sagae.
No, not yet.
Maybe they'll do that on the May 29th.
Maybe it was a depiction, a simulation, but not an actual one.
That is possible. I am just realizing that now, and I might just be making a fool of myself. But
yeah. I mean, it's fine. That's your role here, but it's alright.
No, come on. It's always so rude.
I know, I'm joking. Maybe.
No, Sagittarius A is not out yet. Soon.
Yeah, on May 29.
To be fair, I make a fool of myself by asking stupid questions all the time, so don't worry.
There are no stupid questions.
I make a fool of myself by being 17.
That's the best reason to make a fool out of yourself.
Yeah, at least you have an excuse, right? I don't anymore, so...
I don't understand that. Why do people see age as an excuse for poor behavior? Like, I mean, sure, developmentally, like, I'm a lot less intelligent than you guys simply because
not necessarily. That's not true.
Let's not go into digressing cosmology yet. So no, that was my question, because I know that some people will bring it up. Will say, "Oh, this is just Photoshop of someone's asshole or something like that," and they will think it's a conspiracy. The blah blah blah.
Well, look, it takes 10 years and 200 people to take a picture. It only takes 5 seconds to deny it.
True, but let me just ask you something that...
It's fake.
No, what I'm saying is, okay, was there, as far as you know, was there any sort of double-checking that the technique that was used to, not as much to take... To like receive the photons, but to actually process the data into a picture.
Yeah.
Was it double checked so that it was confirmed it wasn't biased towards showing what they wanted to show?
Plenty. It was checked plenty. That's the answer.
And who checked the checkers?
No one checked the checkers. Actually, the managers checked the checkers.
Conspiracy confirmed.
They have released it.
Who watches the Watchmen?
They have released all the stuff that would allow other teams to double, triple, quadruple, quintuple, sextuple, septuple,
yes,
so on and so forth.
Yes, fine, but who checks that?
The manager.
The check
Who checks the
checker.
managers?
No one.
Exactly.
Yeah, sure. Everything's
It's all
possible.
a big conspiracy. It's all a big conspiracy.
Well, this kind of proves it, right?
It's conjecture.
Also,
that is a straw man fallacy. If I
science is about proof, and you can't prove that it wasn't tampered with.
Well, you can.
Yep.
you can go out and do it yourself.
Yes.
Yeah, well, it's not like I have. It's not like I have 8 telescopes in my pocket.
No, but the data's public.
Yeah.
I still don't have a supercomputer to process it.
I have
Well,
one.
use the
I'll borrow
Einstein.
it.
Use something similar to the Einstein at Home project, then.
Exactly.
Look, I'm not being serious, guys. I'm just provoking Shoba because I know that she's very sensitive about it.
No, it just makes me roll my eyes. Don't worry, you're not getting to me.
I've just had a realization. I'm gonna get teased about this so much when I go back to school.
No, why?
I'm the local science space
Nerd.
guy. Sure. And like whenever something, like in the rare occasion that people are like legitimately interested, there's like this group of people. There's one, I won't mention his name, but the people who actually know me in real life will know who I talk about when I say legitimately the single stupidest person I have ever met. Oh my god.
Look,
He doesn't believe that the moon landing was real because he doesn't understand that you can have a camera on the end of a stick.
Oh yeah, no, I get it. You're talking about Trump?
No, I don't know. Some 17-year-old Scottish kid in living in Scotland would have ready access to Donald Trump. Readily available access to Donald Trump. Because of the fact that we both have Scottish DNA, it's just like I can flip a switch and he's immediately on my doorstep.
Who, Trump?
Yes, I'll do it now.
No, thanks.
Please don't.
Anyway, we are at the end
Yes.
of our allotted time, and this was a great episode. I see that Shoba is raising her hand. She wants to say something.
Yes, I found your quote. It's a good way to finish.
Me?
Yeah.
Yay! I'm overly excited.
Edwin Hubble, 1954.
Wait! You
That's
need
the
to
one.
read it. You need to read it with a proper voice. Wait, let me just do something.
No, don't put reverb.
No.
On,
Yeah,
please.
no. You need
reverb.
You need. Wait. Check. Well, you need to do it properly.
Oh, come on.
Okay. No, let me read it. Let me read it.
No.
Come on.
Come on. Okay, fine. Do it properly though.
Equipped with his 5 senses, man explores the universe around him and calls the adventure science.
That's the one.
Okay.
It's the one.
It's the one.
Inspiring words for all observers.
All right,
Yes.
so let's conclude it with that. Oh no, Selfish Pie, you wanted to say something before we finish.
Yeah, but he forgot.
Oh! Yes, no, I didn't forget. If anyone who is listening is interested in the Falcon Heavy, then today will be the first commercial launch of the Block 5 Falcon Heavy, and it is happening at 6:35 p.m. Eastern Standard Time. Or no, not Eastern Standard Time, EDT. I don't know what it stands for, but that's in an
Eastern
hour.
Daylight Savings Time.
I think that's the one, but whatever it is, it's in an hour. So if you want to watch it with me, I won't be streaming, but I'll be there spiritually. Spirits don't exist, but
Well,
I don't know
we
what
get
I'm on
it.
about.
45
It's
minutes.
on in
it
an
is.
hour.
That is indeed something remarkable. We didn't have really time to talk about it because the topic was another one. But indeed, if you have a chance, you should definitely check it out because that's yet another great step for humanity. Eventually, we will get out there quickly, cheaper, faster. And I like SpaceX myself, so I hope that they will succeed smoothly.
Good luck.
So yeah, I don't think Michael will be covering that though, sadly.
No, it's a little too late. I probably will be watching it too, but yeah, I don't want to broadcast it. I think I will share the link in the channels and everyone can watch it, but we don't need a commentary for that. I think everyone knows what's happening there. Also, it will have its own commentary, so we will be super fluent.
Indeed. All right, guys. This has been Dangerous Cosmology with Dr. Commander Shoba. And thank you for tuning in. This has been incredibly interesting. Thank you again, Shoba, for taking your time after a long, tiring day to take more than 2 hours here with us. And of course, thank you, Michael, for handling the technical side of things. And thank you, Selfish Pie, for being here and providing your brilliant commentary.
Yeah.
I don't want to sound too mean. I actually like Selfish Pie. I'm just
my succulent Scottish speak like. Exactly. That sounded better in my head. I'm gonna shut up now.
Yes.
The way you say now is the most Scottish thing about you.
No.
Thank you.
Yeah.
And of course, thank you everyone who listened in and asked questions. I expect that the news will talk about this thing for days to come. So if you read or hear something that you want to know more about, I believe we can spend some time next week for the leftover questions.
Yes.
Because this is a big thing. We should dedicate as much as we can to answer questions, as long as we have Shoba here, an expert in quasars. So who better to clarify any doubts that we have? So stay tuned. If you have missed the previous episode of Dangerous Cosmology, just check out our repository where all the episodes are stored, including this one if you missed the start.
Yes, I will post the link as soon as it's up on here. Also, you can watch the VOD on YouTube, of course.
So this has been it. As usual, thank you again. This has been Nightfall Zero from the Red Comet. I am getting very sleepy, so I will stop talking now. I will follow Selfish Pie example.
Okay. From my side also, thanks for listening, thanks for tuning in, and thanks for being here, Nightfall, Shoba, and Selfish Pie. And we will talk to you next week with the next show of Dangerous Cosmology. Goodbye, everyone.
Some music now.
Bye.
Bye.